Namaste and Shubhodaya. Myself Pavitra, Senior Scientist at CSIR-4 Welcome you all to the CSIR-4 JIGYASA team organized Vismaya Vigyana YouTube live lecture on topic Seismic Sounds in the Sky, Day 2. I would like to thank the student community for supporting this initiative. Without any further delay, I welcome Dr. Sithartha Muthu Vijayan sir into the forum. Sir.
Thanks,
welcome,
Ms.
sir.
Pavitra, for inviting me again. Now we will go for the second day of session.
Sure, sir.
Yeah. Can you throw? So, welcome all for the second day of the session titled Seismic Sounds in the Sky, Detecting Earthquakes and Tsunamis via Ionospheric Anomalies. So, as I told you yesterday, this talk has three topics. So first one we covered yesterday, that is waves and infrasonics, and today we are going to cover earthquake, tsunami and atmosphere. Then tomorrow we are going to cover the GNSS and ionospheric anomalies. So before going for today's session, let us have a small recap of what we learned yesterday. We started with waves and how the oscillations goes from one place to another without changing the medium or disturbing the medium. Then we studied about longitudinal waves, different type of waves like transverse waves, water waves, Rayleigh waves, and then the acoustic spectra from infrasonics, audible to ultrasonics, then the sources of infrasound. Then also finally we concluded with what are all the ways to observe the infrasonic sound, basically using the pressure variations. So now today we will go to the earthquakes, tsunamis and atmosphere, because as per the session we studied these fundamentals to know that how the energy released during earthquake and tsunami propagates into the atmosphere and how that can be detected in the ionosphere. So before going to our final destination, now this is the time we need to know what are the earthquakes and how that occurs and what causes these earthquakes, and similarly what are tsunamis and how tsunamis are caused and what are all the properties of the tsunamis and how this throws the energy in the atmosphere. So to know that, we need to know about the atmosphere, structure of the atmosphere and things. So let us see that one by one today. Let us start with earthquake and tsunami. First earthquakes and then we will go to the tsunami. Earthquake. So we all might have heard about many incidents of earthquakes. It occurred at this magnitude. Earthquake has occurred on some day. So basically we might have seen that the earthquake occurred at this epicenter or at particular location. We will call that as a epicenter. That is on the surface area where the earthquake is represented. But actually the earthquake occurs at some depth. The depth varies. Shallow earthquakes causes more damage and deeper and also depends upon the magnitude. So the earthquake releases an energy. So this energy propagates radially, and that is why we started with waves, how the energy propagates in different medium in different ways. So the earthquake energy propagates along the earth, and it at different ways. So basically you could have noticed that there is a line here. This we will call as a fault line. So the earthquake occurs typically at faults.
Sir, if I may interrupt you,
Yeah, please.
I have a question. So students would like to know, what do you mean by deep earthquakes and what do you mean by shallow earthquakes? Shallow means at what depth and...
Yeah, generally around 10 kilometers and less will be shallow earthquakes, and further it goes into deep. It goes into hundreds of kilometers also.
So how thick is the lithosphere?
I'm covering that.
Okay.
I'm covering all those things. So to know that, to understand how these earthquakes are happening, especially these fault lines, you can see that. So here the stored energy stored over the period of years will be released all of a sudden. So that is how the earthquakes happen. So what causes this and how this energy is stored and why earthquakes are occurring. So that we need to know. To know that, we need to know the structure of the earth. You see, the radius of the earth is around 6,371 kilometers. And where we are living on this thin part. But beneath, we have different layers. You can see that a layer called mantle here, that covers both upper mantle and the lower mantle, and then outer core, then inner core. So this takes maximum radius, and we live on a very thin crust section. If you zoom it here, that is what it happens here. See, the continental crust where we live on the land, that goes to 30 to 40 kilometer thickness. And the deep ocean, what we are calling, that goes to around 8 kilometer thickness. And beneath, we have lithosphere, asthenosphere, and other areas. We can take this crust into, we can dissect it. So on this very thin layer we are living, and above that, what this blue line is our atmosphere. So the energy maximum of the earthquakes occur in this portion, and that energy is released and it travels all over the earth, and a small portion of energy propagates to the atmosphere. And this crust where we are living, such a thin crust, something like if we boil a milk, we will have a layer over that, and such a small layer over that only we are living, and we think that it's stable, but such a thin crust over that we are living, and this crust has divided into different plates. It fragmented. So that is what this actually shows, of different plates, where here is Indian and Australian plate, this brown one. And these plates are not static, they are constantly moving. See, one of our results here in our CSIR-4 what we computed using GNSS geodesy and the observations made all over the globe, that shows that these arrow marks are showing the velocity or the movement of the place where every GNSS station is anchored. So basically it represents the motion of the plates. So you could see that this is constantly moving, and the length of the arrow depends upon the magnitude of the velocity and the direction it shows, which direction it goes. You could see that it all moving. So because of this motion and the relative motion, one over the other, the plates are colliding, or it moves apart, or it transforms each other, I mean slide past each other. So that causes strain energy, and that energy gets stored over the years, and that gets released as earthquake. And you see this map, actually it shows that from 1st January 2001 to 31st December 2015, totally how many earthquakes happened all over the globe. And the color, actually it shows that the depth of the earthquakes, you can see that it goes even up to 800 kilometers. See, it starts from very shallow, this is the shallow, to the deep earthquakes it goes. And another interesting things you can note that most of the earthquakes, all the major earthquakes, forms on certain boundaries. So these boundaries marks the tectonic boundaries. So these are all plate boundary earthquakes. So other than that, there are some interior earthquakes too. So all these earthquakes throw up the energy, releases the energy. And this energy is propagating in the form of seismic waves. Like you see, this is the focus, and from there it comes. And there are different types of earthquakes. So let us see that first. So this is actually normal faulting earthquake, where the fault line between these two masses, it actually moves apart and creates the earthquake. And this is a thrust earthquake, or the compression motion, compressive motion creates this. So one over the other, like this is what happening in Himalayan region. And the other one is the transform motion, which creates the strike slip earthquake. So this actually slides past each other. The last year, the major earthquakes happened in Turkey are the best examples of strike slip earthquakes. And these earthquakes, as I told, this releases energy, and this energy is moving in different waves. That is P as a primary wave. That yesterday we have seen that how the longitudinal waves are propagating. So this is basically longitudinal waves. And secondary wave is a transverse wave. So that it propagates in the transverse motion also. And in addition to that, surface waves called Rayleigh waves and Love waves are also propagating on the surface of the earth. And this is how the energy is getting propagated from which is released during the earthquake. And let us see a small a real life demonstration, so which shows how these waveforms are. So this is just to show that how these waveforms, just as a recap what we saw yesterday. So similarly, this seismic waves, this is how a seismogram will look like. We will be having a seismometers or seismographs on the specified locations. When the energy passes through that, that gets recorded and that creates a seismogram. You can see that the arrival of P wave first and then S wave, then comes the surface waves. So this is how it looks like. Now, these earthquakes, specific earthquakes like thrust and normal faulting earthquakes, creates a tsunami. It's not only the earthquake, there are other things also create tsunamis, but the major source for the tsunami is the earthquakes. If an earthquake occurs on the sea surface, I mean beneath the sea floor, like this, the energy gets thrown up. And this actually, because of the tectonic motion, that earthquake happens, and this throws up the energy. And that actually moves the water column up. So when the water column is moving up, then the water column falls and generates an internal gravity waves. And that wave starts propagating. And you could notice that here the wavelength is very high, and when upon coming here, the amplitude increases but wavelength decreases. So this is how in the mid ocean you won't see the much of the magnitude, but when it comes on the shore, the amplitude of the wave, height of the wave increases. See, this shows clearly how the waves of the wave characteristics of the tsunami. You could see that at 4,000 meter depth, that is on the deep ocean, normally we cannot find out a tsunami is propagating. That's why those who are sailing in the deep ocean, if a tsunami actually propagates beneath, they won't be even knowing. We can't, in the normal sense, we can't even find out there is a tsunami going beneath when we are floating over there. Because its amplitude is very small, but you see that the wavelength is very high. It's a very long wave. And upon when the depth decreases, could see that the velocity also decreases and the wavelength also decreases and the amplitude increases. The height of the wave increases. So a small wave here, it becomes tens of meters height when it reaches on the shore. So that is why it is very challenging to detect tsunamis when it is propagating in the middle ocean. Only we will find out when it comes closer to the shore. So this is a major challenge. That is why tsunami early warning is always challenging. See, this is the tsunami photograph, real photograph, happened during the 2011 Tohoku earthquake, which created the tsunami on 11th March 2011, occurred in Japan. And in 2004, how this tsunami happened, this animation actually shows that the tsunami generation there. This shows that this red color which propagates, that shows that how the sea floor ruptured. That is starting from the Sumatra to the Andaman at the speed of 2.5 kilometer per second, it ruptured. And this rupture generated the tsunami in the Indian Ocean. Just see, this generates a tsunami on the surface and which started moving towards India, and then it covers the entire globe. See, this is another snapshot of how this tsunami propagates and then it reaches the Indian shore. So this generated major casualties along the coastline, and even now the early warning or detecting the tsunami is a major challenge. So this is one of the reasons where we are studying whether the atmospheric manifestations of these tsunamis can be used for an early warning in addition to the conventional early warning. So as I told that these tsunami waves and earthquakes, when it is propagating on the surface, it throws up, yes, when the wave moves up and down, it actually throws up the atmosphere a little. So when the atmosphere actually, when it is throws up, a similar tsunami wave is propagating vertically up. So when it is going similar to the wave characteristics here, so in the atmosphere, it actually grows in amplitude when it moves to the higher altitudes. So that disturbs a upper atmosphere. So to know that, we need to know the structure of the atmosphere. Just see here, the atmosphere has many layers. You might have studied in your geography and earth science portions of your science. It starts from troposphere and to the upper atmosphere called mesosphere. And this layer is depicted here. So there one layer, there you can see that it goes from troposphere, tropopause, stratosphere, stratopause, mesosphere, mesopause, and then thermosphere. And here comes a layer called the ionosphere. So we will call this layer as ionosphere. And when the sound waves or the gravity waves, when it starts here, it propagates at various speed when we are moving upon at higher altitudes. So we call this layer as ionosphere. So our point of interest is on this layer, ionosphere. So we are calling this layer as ionosphere because this layer is completely ionized. So what is that ionosphere means? What is that ionization? So you might have studied in the science class that there are different states of matter. You might have studied about solids, liquids, gases, and there is one fourth state of matter that's called plasma. So in this plasma state, ionization happens. So because of that, we will always have ions and electrons. So this combination of this are called plasma, and because of the sunlight, when it falls on the layer of the topper layer of our earth, that gets ionized and that goes into a cold state of plasma or a plasma state. So this ionized layer is called ionosphere. This is another depiction of the ionosphere. Could see that when this is the sunlit area, so when the sun shines, the ionization increases, and then the number of this shows that this color bar shows the electron density. That is, we will see we will say the density in the number of electrons. So when the electron density is very high, you could see that high red color. So here the sun ray falls the atmosphere, and hence this is completely ionized and it is in plasma state. So this is ionosphere. So now our interest is how these sound waves or acoustic waves in the infrasonic signal, which is being generated from earthquake and tsunamis, it propagates via the troposphere, and then it reaches the stratosphere, and then further it reaches the ionosphere and disturbs the ions. So our interest is on that, how this disturbs the ionosphere, and that ionospheric disturbances and anomalies, how are we going to detect it? So the question is how this happens. And before that, when we wanted to know how the ionospheric disturbances caused by earthquakes and tsunamis, if we want to know, first we need to know about the dynamics of the ionosphere. The challenge here is the ionosphere is highly complex and dynamic. There are various factors which affects the ionosphere and causes disturbance to it. The challenge is we have to filter out the rest of all the regular changes or the disturbances caused by various sources, and then we have to filter out all those things. We have to find out only the disturbances caused by earthquakes and tsunamis. So that is a major challenge. So you could see that the ionosphere, other than ionization, it is getting disturbed by various factors above the surface of the earth, like the sun rays, solar flares, and the dynamo effects. All those things causes the ionospheric disturbances here. And not only that, because of the regular motion, the equatorial ionization anomaly, we will say a dynamo effect, and that is a regular phenomena which goes on that. So all those things are creating traveling ionospheric disturbances. So all those things need to be filtered out. And now I have told that the earthquakes and tsunamis are generating, releasing the energy, and that energy is propagating in the atmosphere. So how is that happen? So this schematic, this explains how that happens. Just see that a nuclear explosion or any explosion, the earthquakes and tsunamis, this actually throws up the atmosphere and releases the energy to the atmosphere. Two points I am saying. One is releasing the energy, another is just disturbing the atmosphere. I will come to that, the differences in the next slides. But this energy propagates as a wave and it goes into the neutral atmosphere. So let us divide this for our convenience into two atmospheres. One is an ionized atmosphere, another part is the neutral atmosphere. So the lower part is the neutral atmosphere. So where this sound waves or acoustic waves just propagates vertically up, and after reaching the ionosphere, the ionized region, it disturbs. So these disturbances in the ionosphere will be detected. That is our point of interest. So to know that whether this energy is really propagating up, because generally earthquakes and tsunamis are studied on the ground. That is because of the limitation in our observation. So all these observations are tsunami and earthquake observations using seismometers and things, infrasonic network, are anchored on the ground. So all our observations so far were from the ground. So our knowledge about how this small amount of energy which gets propagated in the atmosphere is really reaching the upper heights. So that is bit elusive. It was not very clear. So that is why we were studying using all the observations carried out on the ground. So now to know that whether this really happens, there are series of efforts, but problem is the density of the observation. The ionospheric observations where the density is not very high, that is at few points the conventional ionospheric observations were happened before the satellite era. And the GNSS geodesy, which I will be covering in the next session, that actually creates the opportunity to observe at various places and in high in number. So we started initially finding out the disturbances in the ionosphere. But the question is whether it is really because of the acoustic waves, whether it really propagates in the neutral atmosphere. So how to know that? So basic interest of this, the neutral atmospheric propagation of the energy starts after the Second World War. So after the nuclear detonations and the nuclear bombs exploded in Hiroshima and Nagasaki and the World War II ended, after that many countries started making nuclear bombs, and the nuclear test ban treaty was also formed. So other countries, each country wanted to know whether the enemy country is testing the nuclear bombs or preparing nuclear bombs. So the one avenue was infrasonics. So that is why the observation started. The balloon based observations soon after the World War were started to find out whether Russia is really making the bombs. The US started that. But some of the observations were successful and some couldn't give very good results. So after that, infrasonic network was formed and nuclear policing was started. But then again, a renewal in the interest came after the 2004 tsunami. So this is one experiment done in Jet Propulsion Laboratory, NASA. So to know that how these seismic waves are propagating in the atmosphere, a balloon based microbarometer studies were taken up. So in Nevada, that's a desert in United States of America. So a seismic hammer was established. A seismic hammer here is nothing but a 13-ton mass. A 13-ton mass which is supposed to generate an artificial seismic signals by dropping it or hammering it, continuously hammering a 13-ton mass. So they could generate around 0.19 joule of energy, and totally 108 shots were done. And this energy, what it generated, an artificial seismic energy, and in a balloon, like lower aerostat and upper aerostat, you can see that a barometer was suspended in a balloon so that it could sense these signals. So basically to know that whether we can really sense these signals, whether these signals, seismic signals are really propagating in the atmosphere. So this experiment was started in 2007 sometime. So this shows the instruments on the balloon. Could see that at a height it was this shows that difference between upper and lower aerostat barometer and the height of the balloon, and the results was very good. You could see that here this graph actually shows the time of the hammer strike and after the propagation time, which matches with the velocity of the sound at the given pressure and temperature, and after the delay time, both upper and lower barometer, aerostat barometers picked up the signal. So this is a clear demonstration that the acoustic waves, seismic earthquakes are generating acoustic waves, and these acoustic waves in the infrasonic domain, it actually moves up in the atmosphere and it reaches the heights. So this is another way of looking the signal, because we need to know what is the frequency of the signal. So this is the wavelet transform of the observed microbarograph signal. You can see that, as I told you, the pressure variations are being used to detect infrasonic sound. So this is the in time how the pressure varies. And this color panel, this shows the frequency versus time. So you could see that exactly during that time, and with the frequency of in the infrasonic domain, that is less than 20 kilohertz, sorry, less than 20 hertz, this is here. So we have picked up the signal. This is clearly in the infrasonic domain. So they have picked up. So this is a very good experimental proof that the acoustic signals generated by the earthquakes are propagating in the atmosphere. And similarly, the tsunamis are also propagating releasing the energy in the atmosphere. So this is bit different than the regular acoustic waves. This is acoustic gravity waves. That means, as I have told you in the previous animation, the tsunami, when it propagates, it throws up the atmosphere a few centimeters up and down, depends upon the wavelength there. So when the wavelength is very high, a large amount of air mass has been thrown up. So this air parcel just moves up and the gravity restores its back. You might have studied harmonic oscillation in your school science chapters. So like the harmonic oscillation, so this moves up and falls down. So this actually generates a wave which is restored by the gravity. That is why we are calling this as a gravity wave. Please do not confuse this with gravitational waves, which is separately studied in physics. That is different, gravitational waves. This is the gravity waves because the restoration force is a gravity. And this grows up in the atmosphere a few centimeters here in the on the surface. When it is moving to 350 kilometers or 400 kilometers, it goes to kilometers of oscillations there. So it completely disturbs the electrons and ions in the ionosphere. So that is what our interest is. So this is a combination of both acoustic as well as gravity signals. That is why these waves generated by tsunamis are called acoustic gravity waves. And all the waves, then naturally the question comes whether all the waves which is happening in the ocean, whether that anyhow that will throw up the atmosphere, whether that goes and disturbs the ionosphere. No, here actually only infrasonic waves with very high wavelengths and low frequencies could reach the higher altitudes of the atmosphere. So atmosphere actually works as a natural filter. That's because there is one called Brunt-Väisälä frequency, which when you are reaching the higher standards, you will understand. Right now you just know that there is a Brunt-Väisälä frequency, and that actually will not allow all the higher frequency sound waves. So only low frequency and high wavelength infrasounds can reach the ionosphere, which ranges from around 3.3 to 1.1 millihertz. So this was observed after the Peru tsunami and the 2004 Indian Ocean tsunami very recently. Before that, Alaskan earthquake and tsunami when happened in 1962, if I remember right. So that actually disturbed the ionosphere, and few observations are there. Actually, it started in 1974. I'm sorry if I remember. So that is how the ionospheric disturbances were first detected. See, this animation actually shows that how this throws up. You just see that the waves are propagating here. So these waves will throw up the atmospheric column. The atmospheric column will oscillate up and down, up and down. So that generates the atmospheric acoustic gravity waves. These acoustic gravity waves will reach the ionosphere, and if we are having a GNSS satellite here and GNSS receiver here and the satellite here, if it cuts across the signal ray path, we could detect that. So how are we going to detect this in the ionosphere? I have told that global navigation satellite systems are simply global positioning systems which sends this microwave signals from there, and when it is cutting across these acoustic gravity waves, we could decipher that using normal GPS which you will be using in your mobile phones. That is the GPS which you are using. That in sophisticated form, the geodetic receivers we will be placing, that will be used to pick up that signals to find out when the tsunami propagates in the ocean, how the similar disturbances propagating in the ionosphere, whether we can use it for early warning. So these are all the challenging questions. So to know that, we need to know about the GNSS technology and how we are detecting that in such signals in the ionosphere. So that we will be discussing tomorrow. And this is another simulation. This is a modeling work, theoretical work. This actually shows that done by Inchin et al. In 2021. This model clearly shows that how this tsunami, which actually propagates the waves up, acoustic gravity waves, and it reaches the different heights. So this is the theoretical one, and at CSIR-4 we have measured these disturbances using GPS satellites and its observations. So that we will see tomorrow. So far we have completed the fundamentals of the waves and infrasonics, and now you hope you might have got a clear idea about how earthquakes occurred and how that generates tsunamis and what are the atmosphere and how this infrasonic sound propagates in the atmosphere. So tomorrow we will come with results we got using global positioning systems while detecting the different earthquakes and tsunamis. So that is reserved for tomorrow, and that will be covered in the tomorrow session. So thanks a lot for your listening, and please come back and join tomorrow. So we will show the real observations what we made at CSIR-4.
So before we conclude, there are few terms that you mentioned during your lecture. Let's clear it to students what they actually mean. First thing, when the artificially induced the earthquake, can you go back to that slide?
Yeah.
Yeah. Here you're talking about an aerostat. So it will be nice if you can explain what does an aerostat mean.
This is actually a balloon-borne device. So there is a balloon, hot air balloon. So the instruments what it's shown here, barometer is nothing but to measure the microbarometer is to find the pressure variations in a micro scale. So this will be placed in the balloon, hanged in the balloon.
Okay.
And that balloon will be sent up to, actually this, since it is an experiment, it is of 300 to 400 meters height. It was sent. And these barometers, when you are hammering here, usually the seismic waves what we will be using, there were ground networks also. Okay. That ground networks, usually it propagates on the ground, seismic waves, S waves and P waves, all those things like a same seismograph. And a small amount of energy, I told that this actually propagates in the atmosphere.
Yes.
So that actually at this height, these barometers has detected.
Okay. Now
I hope it this clears.
Yes. Yeah. So the next thing is when you were mapping the movement, you spoke about wavelet transform.
Yeah.
That is something we study in.
I might not have studied in school.
So let's just tell them what exactly is a simple wavelet transform means.
So basically this is, I'll put it in a different way instead of going for wavelets. So this is just giving a time versus displacement graph. So this is amplitude versus time. So normally they might have studied in the chapter motion, time versus displacement graph.
Yes.
So we will take like that. So one is the time and y-axis is the amplitude here, the amplitude of the wave motion.
Yeah. So how a wave moves.
How a wave moves.
Yeah.
So that is what this actually shows. But this one, the next one, we are actually transforming it. The Fourier transforms, initially the Fourier's one, it helps, and then another one is a wavelet transform that they will study in colleges what it is. But we can actually transform instead in the time versus frequency domain. So from this we will find the frequency of the wave. See here, we can find within a given time how many total waves passed through it. So that will say the frequency.
Yes.
And this is a composite wave, not a simple wave. So it contains multiple frequencies. So we will actually transform and find out the frequency. And when that frequency occurred, we will be plotting it. So in a given time, when that frequency occurred.
Okay.
So this is basically a time frequency graph. So this actually says that what are all the frequencies. You can see that it's not a single frequency.
Yeah.
It's a multitude of frequencies, multiple frequencies. So it's a very low frequency to, it's all infrasonic only, but you can see that the band of frequency here. So this color scale actually shows the power of that frequency spectrum.
Okay. So I hope that clears the question.
It may be little complicated for school student as of now. Right now you just take it as such. Over the period when you are studying, you will understand.
Okay. So next thing is we started talking about tsunami. We all know it's when the earthquake occurs in the ocean, it triggers tsunami. But what is the minimum magnitude that
no,
is
it is
required?
not the magnitude. No, not only the magnitude. It depends upon what kind of motion. So that is what initially, while talking about earthquakes, I have explained the different type of earthquakes are there.
Yeah.
So thrust, transform.
Yes.
So this one. Yeah.
Yes.
This one. So mainly the normal and thrust faults that generates the tsunami. Not only this, landslides inside the ocean that also triggers tsunami, and any asteroid fall or other causes will create a tsunami. And recently, one recent science paper has come, very recent in this month. Last year, it was about the avalanche or major landslide happen in Greenland. So because of the climate change, a massive landslide occurred that generated a huge tsunami. Since many are not living there, it didn't affect life, but that generated a tsunami. So landslides also causes tsunami.
So basically, when a huge volume of water in the ocean gets dispelled, it generates a tsunami. Yes. Okay. Thank you, sir. Thank you for this session today. We'll meet tomorrow at the same time. Thank you for joining, everybody. Thank you very much. Have a nice day.
Thank you.
Thank you. Yes. So how many views?